Thank you very much for the introduction. And I'm very happy to have the opportunity here to present our work on Supernova Axion scope, which is used for the direct search of supernova axions. Okay, oops. Okay, so this talk is based on my previous work, and it is going to be published in JCAP. So as Masaki and Ivana mentioned, the axion model is a very attractive physics model because it not only solves the strong CP problem, but it also offers attractive dark matter candidates and probably related to baryogenesis. But more importantly in this talk is that it couples to nucleons, photons, and leptons in various ways so that we can search for it with many different methods. And the method I will focus on is the Axon Helioscope. So the basic idea is the following. Depending on the axion photon coupling, axion can be abundantly produced in the sun through the Primakov process. Then if we point the helioscope towards the sun, the axion would travel into the bore of the helioscope. Then it can be converted into X-ray photons by the strong magnetic field inside the helioscope. And actually, the CAST helioscope have provided us some stringent bond near the EV level that exclude part of the QCD axion parameter space. And future helioscopes, such as IAXO, will push this bond even lower so that more parameter space in the for the QCD axion will be probed. But of course, the sun is not the only object that might emit axion. So we can also imagine pointing the helioscope towards a supernova. And since the axion can be also produced in the supernova through the Bremsstrahlung process, there is a probability to detect the axion from the supernova. Note that the temperature of the supernova is at the level of mega electron volt. The converted photon will be gamma rays, but not X-rays. So we will have to detect it with gamma ray detectors. So our proposal is very simple. So we just propose that we install a gamma ray detector at one end of the helioscope that is opposite to the X-ray detector. Then usually we just make the helioscope pointed to the sun as usual to search for solar axions. But if we somehow know that a supernova is going to explode, we can turn the helioscope around and to face the gamma ray detector to the supernova. And hopefully we can detect supernova axion transfer to gamma rays in the gamma ray detector. Oops. So the rest of the talk, I will try to answer the following questions. So when shall we expect a supernova explosion? And which supernova progenitor shall we look at? And whether it is really possible to point a helioscope towards the supernova? And what is the detection prospect of doing so? So let's start from the when question. So it has been shown that when a supernova progenitor approaches its core collapse phase, its emitted neutrino flux would increase over time. And eventually, it will reach a level that it can be detected by current or future neutrino detectors. And actually, according to this very nice review, it shows that even though the pre-supernova neutrino flux is very model dependent, and even if we consider the most pessimistic model, the pre-supernova neutrinos can still be observed in the running detectors such as Camland or Super-Candidates for supernovas within 300 parsecs and about 1 hour before the core collapse. And the situation would be much improved in the proposed future detector Juno. So in this case, it can detect these pre-supernova neutrino from the source within 500 parsecs and about days in advance of the core collapse. And what is better is that these warning messages will be included in the updated Supernova early warning system. So if we receive such warning messages from this system, we can point the helioscope towards the supernova and then just wait for its explosion. So here I show a list of nearby supernova with mass larger than 10 solar mass and within a distance of 250 parsecs. This criteria is basically chosen so that the pre-supernova neutrino can be detected. There are only 6 of them, and of course they are very bright stars in the night sky. 3 of them are blue supergiants, and 3 of them are red supergiants. Well, maybe I should note that most of the observed supernova are from red supergiants. But we do know that the supernova 1987A was a blue supergiant, so we also include them here for completeness. And actually, their distance to the Earth is slightly closer than all the other red supergiants. So they have better chance to get detected. Um, so if Juno was not operating during the explosion and we only have Camelot and Super Camelcande, we would not be able to get the angular resolutions of the source. So in this case, we will have to pick one out of the 6 candidates just by chance, but this is not a low probability already. And if Juno was running at the time of the core collapse, we will have the angular resolution of about 60 degrees. And in this case, we will be able to tell Alpha Orion or Epsilon Pegasus apart from the other candidates. If unluckily, the presumed supernova neutrino come from the lower right region here, then we will have to pick one out of the 4 candidates by chance. So now that we know what are the possible candidates, the next question we want to answer is, would it really be possible to point the helioscope towards the supernova? So since the helioscope were designed to chase the sun, it does not need the mobility of rotating freely in the vertical plane. And take IAXO as an example, it is only allowed to rotate up or below the horizontal direction by 25 degrees. And in this figure, we show the time window in a day where the IAXO helioscope is able to point at the supernova. And this is shown in the dark blue region. And we see for most of the supernovas, the IAXO will be able to point at them at 50% of the time in a day. And if there will be some mechanical upgrade to the IAXO so that this rotation angle can be increased to 50 degrees, then the region will be increased to the light blue region, which is 100% for 4 out of the 6 candidates. And if we get even greedier and assume that there is another helioscope at the other side of the Earth, such as in Tokyo, then the coverage of the 2 helioscopes will be able to compensate each other. Okay. So I hope that I have shown you that it is possible to point an helioscope at a supernova at the right time. And now let's talk about the detection perspective of the supernova supernova axions. So in this plot, I show the 1 event or 100 event contour for the setup of IAXO-based supernova axion scope for axions with KSVZ-like coupling. So the blue curve is shown for Spica, and the red curve is shown for the Betelgeuse. So these two candidates are chosen because Spica is the closest one to us, and Betelgeuse is the furthest one to us from the table. So this gives us a rough idea of what is the range of possible number of events in this case. So there are two important features I want to mention here. The first one is that we know that the axion field and the photon field will start to lose coherence with each other for high axion mass. And this is the reason why helioscope tend to lose its sensitivity for heavy axion masses. And this is most evidently in this expression for the conversion probability. So the loss of coherence occurs when the sign factor is of order 1. And this is dependent on the momentum transfer Q, which is dependent on the axion mass and the axion energy. For the case of the supernova axion, the energy omega is much larger, so that the loss of coherence happens for a much larger axion mass, and that explains the higher mass where the supernova SNscope start to lose its sensitivity. And because of this, SuperNova-scope is much sensitive than the helioscope in the large axion mass region. And actually, it would be able to cover all the parameter space for the QCD axion with mass larger than 0.01 electron volt. Another feature is that for lighter axions, which is in this range, the sensitivity for helioscope and supernova's axion scope is roughly the same. And if the axion parameter happens to lie in this range, such as in the case inferred by the stellar hints, which is the parameter that is inferred by various stellar cooling anomalies, such as those from the white dwarf, as mentioned by Masake. In this case, it is likely that both the solar axion and the supernova axion would both be detected, and the supernova axion scope becomes a tool to study the interior of the supernova. And so here is the brief summary of what I just talked about. So I hope that I have convinced you that the news may focus the next nearby galactic supernova within 300 parsec. And so that we will be able to point a helioscope toward the supernova. And for the proposed setup of IAXO, there will be 50% of the time when it is able to point towards one of the supernova. And as for the detection prospect, the supernova scope probes much heavier axions, and for light axions, it is probable that both solar and the supernova ones will be discovered. I missed up some the technical detail because of the limitation of time, such as the implication from Supernova 1987 A-bound, the detector design, etc. But I will be happy to answer any question on them, both in the question section or in Slack. And hopefully we can see a nearby supernova in our lifetime. And that's the end of my talk. Thank you, and I'm happy if you have any question.